recapping from 2 years ago as to what we were wanting to do. We basically wanted to understand whether or not we could represent paddock scale soil water variability robustly in such a way that it could inform decisions. And the main reason for that was that most people have got a soil moisture probe, if they've got one at all, and that might give you nice information about the little hole in the ground where it's installed, but you actually want to know what's going on everywhere else. And the same might apply to the rest of the farm. And of course there's another question about whether or not being able to do that is useful. We identified a few different ways of doing that, starting with at the bottom of the slide with the complex one. We came up with a procedure using cumulative NDVI, the growing degree days and the cumulative net precipitation as a means of trying to extrapolate away from the probe. And then there are some simple ways as well, just using simple correlation of moisture at the probe to moisture at particular locations. And those methods, the utility of those methods or the ease with which they can be implemented depend on things like careful sampling and or ability to identify soil or crop production variation in terms of zones and so on. This is an example from Dan Adams' farm. So during the season, as the crop grows, the NDVI increases, reaches a plateau, and then it starts going down again. We can smooth out some of the variation in that by collecting a lot of images through the season and come up with this cumulative NDVI curve here, which we then integrate with the cumulative temperature and rainfall, and that allowed us to extrapolate over the probe. So here's an example again from Dan's farm at a 300 millimeter depth in September. You can see here the correlation's not perfect, but it's not bad. And here we've got the actual and modelled trace of the probe, and that allows us to estimate soil moisture. But pretty much everywhere and every time that we've done this, the variation in moisture on any given day down the profile is greater than the spatial variation within the paddock. So that raises a question in my mind as to whether or not knowing about that spatial variation necessarily helps inform a decision made at a given point in time. So that was the more complicated way of doing it. Then in terms of trying to identify some correlations between points in a farm or a field and data at the probe, we wanted to identify some zones. And here's an example from Todd Matthews' farm. We've got yield maps from all these different paddocks. All of these legends are slightly different, and you can see that the harvest of this area is split up into a number of different harvest events. So hopefully the calibration of the yield monitor doesn't change between those harvest events, but just in case it does, we normalise everything on a per harvest event basis to standardise the data, and then we start putting it back together again. So here's the normalised yield for all of those paddocks for the however many years, 7 years it is that we've got data for. You can see that some paddocks obviously are in fallow, and this one here is the focus paddock, and we wanted to adjust everything back to the focus paddock, so we adjust all the data back to the equivalent of the mean yield in 2020 in this paddock, and then we can characterise these zones and understand the relative performance of the zones, and then look at the soil moisture at all these different locations where Jake kindly took soil samples for us and compare to the value at the probe. But actually doing that, turns out at Todd's place, isn't very useful. So you can see we've got the lower yielding areas in orange and the high yielding areas in green, and yet they're all jumbled up here when you put all the data from all the sites and all the depths together. And even if you just go to just a single depth, there's no clear discrimination in soil moisture content between those zones, which probably says that soil moisture content is not actually the main driver of the difference in yield between those zones. At some locations it works quite nicely, you get a good relationship between the probe and a different place, and in other places it doesn't work quite so well. I think one of the main problems with this was that we're a bit constrained by data. We really only had a relatively small number of times to calibrate this against. We focused a bit on Geordie's paddock front southwest, and we'd known about these zones for a long time, courtesy of a project that we had in the mid-2000s. and the more recent yield data confirmed that these zones were about right. So we've got, I haven't got the elevation model here, but basically these lower yielding areas are in lower lying parts of the landscape. And we'd always thought that these low yielding areas are due to sodicity. And what we did was we had a number of sampling points throughout effectively on a transect running north-south down this paddock, and we wanted to see whether or not the information from the probe and the actual soil moisture information from those different locations might help Geordie make a better decision than he could make without them. These are now soil moisture characteristics determined in the lab using a pressure plate equipment, and they're arranged in the same north-south order of these points. And you can see that actually there's not really much difference between them. If you just look at that, roughly the bucket size is pretty much the same based on this analysis. And so, as I say, the soil analysis we'd always thought in these low-lying areas was sodic, and it is, but it's also sodic in the good yielding areas as well. And so that suggests to me that rather than sodicity necessarily being the constraint to yield, and Geordie and I were talking about this last night, these high yielding areas he reckons are pretty good. So even though they're sodic at depth, that sodicity doesn't seem to be presenting too much of a limitation, but the low-lying areas are probably getting waterlogged at the beginning of the season, which is what's causing the problem. So in some respects this is a perverse outcome in that having access to this good soil moisture information allows us to better understand that what we thought was the constraint probably isn't the constraint, but lets us say something more sensible about what we think it actually is. The other thing about this is that we had the information at the probe as well, which was based on the site characterisation that Mandy's team did. So here we've got the soil moisture data for the dry and the wet end based on the field characterisation, and this is the stuff based on the pressure plates expressed in this case in gravimetric moisture content and here in volumetric moisture content in millimetres. And you'll notice that the shape of these is pretty similar, but this lab method appears to be greatly overestimating by comparison with the field characterisation what the actual soil moisture content is. I don't expect anybody to look at this table in great detail. The important bit is this number here, which is the ratio of the field measurement to the lab measurement, which tells you that the lab measurement is probably overestimating moisture by about 0.6, or sorry, the field thing is 0.6 of the lab thing. And so that allows us to then work out what we think the bucket size is, either factoring in sodicity as a constraint or ignoring it on the basis that it's not a constraint. And so if Geordie was to go, for example, to this location here in one of the good parts of the paddock, collect some soil samples, chuck them in his oven, and he might measure the gravimetric moisture content to be about 28% at 20 centimetres and about 32% at 40 centimetres depth. With this pressure plate information, and bearing in mind that doing that gravimetric moisture content is easy, you just chuck it in the oven, he would know that his bucket was about half full. And then based on the information in that table, he could then say, well, if we're not worried about sodicity, he'd have about 185 millimetres of water, and if he was worried about the sodicity at depth, he'd say, well, he's got about 103 millimetres of water. That 185 millimetres, if you believe there's 22 kilograms of grain per millimetre, is about 4.1 tonnes per hectare of yield. From that NDVI-based stuff, we think we can estimate spatial variation in soil moisture using data from a probe and cumulative NDVI. But in my opinion, and I'm happy to be corrected on this, but in my opinion, I don't think that really adds markedly to the farmer's toolkit, because if you go into your paddock, say at GS31, and it's wet where you're standing, it'll be wet somewhere else in the paddock probably. So in terms of making a targeted fertiliser decision, it's unlikely to make a difference. So I think the real value of a soil moisture probe is in helping people understand how this year is different to last year or a couple of years ago or whatever it might be. And the other weakness of that NDVI method is that it can't inform a sowing decision, because obviously with no crop in the ground there's no NDVI. Some of the uncertainty around the probe performance is obviously an issue. We can generate these rules of thumb. The case of Geordie's paddock, it's certainly given us some useful information. But if you want to do this, you've really got to understand the soil variation and or the management zone arrangement in terms of crop performance. So that needs some effort on the part of whoever's doing your mapping, because adjusting those yield maps is quite straightforward when you know how to do it, but it's a bit confronting if you don't. And I think this commitment to collecting good soil moisture data through the season is really pretty critical. The merits of doing any of this stuff depend on what you want to use the information for. We really need to have some clear thought about what it is are we going to want to use this information for.